Hello, this is a video on how to do ANOVA using SAS. Now, I'm going to make this really simple. We're going to test, I'm going to use a variable that we generally wouldn't test, but we may want to know if there are age differences in body mass index. But I'm just using this because that's a generic continuous variable, age. Because in your assignment, you have different variables. You have self-esteem, perceived physical appearance, and third variable. I can't remember what the other variable, depression, right? So those are the three variables you're using. Okay. But here, as you know, I created this four-level BMI variable, cut into quartiles, and we're going to compare individuals just again for this purpose on age. So let's just talk about the structure of this code here. It's proc, it's got its procedure ANOVA. My data set is located here. This is my library, and this is the data set. I use a class variable. A class variable tells me that I have this division by the four levels of BMI. So I classify people by the different levels of BMI. So this is an ANOVA is like a regression. It's a general linear model, basically, and you have an outcome and a predictor. In this case, our predictor is quad BMI and our outcome is age. So what we're saying is we're going to predict age based on these four levels of BMI, right? So we're partitioning the variance in that way, right? I'm also looking for information about means post hoc comparisons. Now, this is going to be a simple one, and I decided to use the Bonferroni comparison, although there are different comparisons. SAS has when we have unequal variances. I just did this recently for somebody where we had unequal variances, and I actually prefer to use the GLM command or procedure, but I don't want to get into that. So we're gonna assume right now that not assume, we're just gonna use the Bonferroni correction. So all of our results are corrected. Post hoc comparisons are corrected using the Bonferroni correction. So we'll just be comparing every possible pair in this. And then I'm also providing confidence limits for the differences here. For your assignment, your job is to provide, well, to complete certain tables. You're going to have, as always, you're going to have a descriptive statistics table. Using the frequency command, you can get the sample size for each level of BMI. Again, you can use a class statement as well. But we can get four different levels. Well, actually, yeah, this is just a frequency statement. I'm sorry, this is just a frequency statement because BMI is already a categorical variable. And then for depression, I don't ask you to give me the different levels by the means by the different levels. I just want the actual means. So you can use proc univariate here, right? And just get the means and the standard deviations. But in general, when we do analyses, we always start by providing descriptive statistics. And the next step will be to complete these tables. So you just want to plug the numbers into these tables. So, and tell me if we have statistical significance, right, using these asterisks. So you put them next to whatever the, I guess, whatever the result is. Well, honestly, if you have the p-value here, you're okay. So we'll just do that instead, right? But I mean, I tend to use these anyway because when we write manuscripts, we often highlight where we have statistical significance using these little asterisks, and we provide a table to identify what each number of asterisks means. So we're going to do that for depression, for self-esteem, and for physical appearance. And then in the end, we're going to interpret the result, including the correct post hoc comparison. Okay, so let's take a look at we're going to run this model for age. So let's go ahead and do that. So we do the proc ANOVA. So like, here's what my results look like. It tells me here's my class. We have these different values, 0, 1, 2, 3. So there's four different values, four different levels, excuse me. And then we have 393 observations, the number of observations used. We sometimes we have missing data for various reasons. Could be that we didn't have BMI on everybody or age, and we probably had age in everybody, but we may not have had BMI on everybody. So this is the table that you're replicating in your results. This is the same table as you'll see here, right? This is the same table. It's structured the exact same way. Essentially, you're just copying that information into that table. That's your standard ANOVA table. You see it has the degrees of freedom based on the model. Remember, it's K minus 1, the degrees of freedom, the within degrees of freedom, or the error as you call it here. We have the total. We have the sum of squares due to the model, sum of squares due to the error, the mean squares, and the F statistic. So everything you need is here, right? Okay. And it gives you a p-value. So in this particular analysis, if we were using alpha as 0.05, we would have a significant difference in age based on body mass index. Although ANOVA, as you know, is an omnibus test, so it doesn't tell us where the differences are. That's why we do the post hoc comparisons. Gives us an R square as well, which is cool. We don't need this. I'm not asking you for figures, but it's nice to see what things look like. You can see where the means are, right? And you get these nice box whisker type plots. All right, here we're looking at the Bonferroni test results. We're looking at comparisons, so comparing group 1 to group 3, group 1 to group 2, group 1 to group 0, and we're looking for significances, right? We look at the asterisks again right here. So 3, and then it's going to have its own code. A comparison significant at alpha of 0.05 are indicated with these three, right? Asterisks or asterisks. So that means 0.05, whereas in my example, I said 0.01, but it's okay. You can leave that there. Uh, so you're going to indicate a group. So this would say like what's group 1? That's low BMI or I forgot what I call that level of BMI. Let me just check. So this is 0, 1, 2, 3. So moderate would be 1, right? So moderate BMI would be 1. So here we have difference between 1 and 0, moderate versus low BMI. So there's a difference. Moderate minus low. Difference is 0.23401. Not very much. This is that's actually a difference between the two means, right? And you'll see that the minimum is 0.01 and the maximum is 0.45785. So there's a significant difference there. There's also a significant, well, it's the only significant difference in age, right? So again, this is a totally, you know, dumb example. I'm using age here. Normally we wouldn't do that. However, you're going to do your analysis with your specific variables and you want to indicate where the differences are. But note that this is 1 versus 0 and this is 0 versus 1. So they're basically saying the same thing. In this case, it'll be negative. In this case, it'll be positive. Just make sure that you're not repeating the same result twice. So that's what I'm looking for here. And yeah, that's it. I wish you well. If you have any questions, please let me know.